In this lecture, I'm going to discuss the reasons behind the various ways objects move. In the previous chapter, we talked about the description of motion through distance, acceleration, velocity, time. Now we're going to talk about what makes objects move in a certain way. And so the main concept in this chapter is the concept of force. So force is, in general, a pull or a push. For example, pushing a shopping cart is applying a force that is a push. Pulling on a rope or a cable is a force that is applied as a pull. Forces act through direct contact or from distance. Examples of contact forces are the force of friction, the force of tension in a rope or a cable, the elastic force in a rubber band or a spring, and the normal force which arises from the reaction of a surface on which an object is resting due to its gravitational weight. And examples of forces that act from a distance are the gravitational force, the electrostatic force, and the magnetic force. Force is a vector quantity. It has magnitude, how much of a force was applied, and also direction. Was the force a pulling force or a pushing force? For example, we say we are pulling an object towards us, or we are pushing an object away from us. So we apply force with certain magnitude, but also in a certain direction. So force is a vector quantity. In the metric system, the unit for force are the newtons. The abbreviation for the unit is capital N. And in the imperial system, the units for force are pounds. And everybody is familiar with the abbreviation for that unit. So when we discuss forces, depending on whether the discussion is done with metric units or imperial units, the unit for force will be either newtons or pounds. We are going to deal with forces a lot through the entire course, so it is an expectation that everybody knows what the units for force are in both measurement systems. So one more time, newtons in the metric system, pounds in the imperial system. And it doesn't matter which kind of force we are discussing. It can be any of those forces that I listed above. Still, in the metric system, the unit is always newtons, and in the imperial system, the unit is always pounds. The principles behind how forces affect the state of motion of objects in nature are described by Newton's three laws. So we are going to start with Newton's first law, which is also known as the law of inertia. So let's read the statement of Newton's first law. A body that is in motion continues in motion with the same velocity, which means at constant speed and in a straight line, and a body at rest continues at rest unless an unbalanced or outside force acts upon it. So let's first talk about the first part of the statement. A body that is in motion continues in motion with the same velocity, which means at constant speed and in a straight line, unless an unbalanced or outside force acts upon it. So what was velocity? Velocity was the speed with which an object moves in a particular direction. That means that if the speed changes, or if the direction changes, or both the speed and direction of motion change, we are now discussing a different velocity. Since velocity is a vector quantity with magnitude, meaning how fast an object is moving, and direction of motion. Once one of those two properties or both change, we now are talking about a completely different velocity. You can agree that there is a difference between 25 kilometers per hour north and 25 kilometers per hour south. And of course, there is also a difference between 30 kilometers per hour north and 10 kilometers per hour north. They're different things. And so, for an object that initially is moving with certain velocity, let's say 25 kilometers per hour north, if we leave that object on its own, without any influence, this object has no reason to change the way it's moving. It will continue to move with 25 kilometers per hour north indefinitely. The only way this way of motion can be changed is by applying an outside or unbalanced force on that object. So imagine that you have, you're pushing a cart, and this cart is moving with constant velocity of 0.5 meters per second. The only way you can make this car slow down or speed up is if you apply force to that car. You're either going to push in the direction of motion, which will make the car speed up, or pull on the car so it slows down. Or you can make this car take a turn by pushing on this car from the side. So that would be the unbalanced force that will change the way the car is moving. So we can sort of summarize that the first part of the statement of the first Newton law is for moving objects. It discusses moving objects. Now let's look at the second part of the statement. So the second part of the statement states that a body at rest continues at rest unless an unbalanced or outside force acts upon it. This one is pretty straightforward to understand. If we have a stationary object, let's say a 2x4 laying on the floor or on the ground, this 2x4 has no reason to move in any way or in any direction on its own. There is no unbalanced force that acts on it. However, if somebody decides to pick it up, now an unbalanced outside force is applied to this 2x4, to this object, and now this object is no longer at rest, it is moving. So objects at rest, left on their own, have no reason to move at all. They will remain at rest unless an unbalanced or outside force is applied to that object. So the second part of the statement of Newton's first law is valid for stationary objects. And those two parts are connected. We can have an object at rest, an outside force is applied to that object, and the object now starts to move. If during that process of motion no force is applied to the object, it is going to continue to move with the same velocity, meaning with constant speed and in a straight line, until another unbalanced force is applied to it. And on another hand, we can have an object that's in motion, but then it stops at rest, and then unless an unbalanced outside force is applied to this object, it will remain at rest forever. So the two statements can be used together, depending on the situation. Now, if an object is at rest, and it's not moving, does that mean that this object is not under the action of any forces at all? No, that is not correct. The object can be under the action of multiple forces at the same time, but as a result, the object is not moving because those forces cancel each other out, and therefore there is no unbalanced outside force acting on the object. The same is true for a moving object. which is moving with constant speed and in a straight line. There can be multiple forces acting on this object, but since they all balance out, there is no unbalanced force that's acting on the object, and therefore it will continue to move with constant speed and on a straight line. Here is an example of an object that is resting on a surface. So this is a calculator that is resting on the textbook here. Okay, so this object is at rest, the calculator. But that doesn't mean that there are no forces acting on it. There are actually two forces that are currently applied on this calculator. First, we have the weight of the calculator is pushing down on the textbook, and as a result, the textbook is pushing up against the calculator with the same force by magnitude, but opposite in direction. And this force is called the normal force. So the two forces, the force of weight and the normal force, are equal to each other, directed in opposite directions, so their effect cancels, and as a result, the calculator is stationary. So just because an object is not in motion, it doesn't mean that there are no forces acting on it. It only means that there is no net or unbalanced force that is acting on this object. Newton's first law essentially describes the resistance of an object to change the way it moves, or the resistance to change in motion. And this resistance comes from a property that is called inertia. Inertia is defined as the resistance to change in the state of motion of an object. And again, the state of motion would be the object is at rest, it only has velocity of 0, or the object is moving along a straight line with constant velocity. So the same speed, not changing direction. And inertia is a qualitative property. Inertia cannot be measured. We do not have a way to measure inertia. But inertia is related to the mass of objects, and the mass we can measure. So how is mass related to inertia? Well, mass is directly related to inertia, which means that if an object has a large mass, it's going to have big inertia. And if an object has a small mass, it's going to have small inertia. So what does that mean in practical terms? Well, picture you are pushing a shopping cart, which is empty. And so this shopping cart has small mass, and therefore it has small inertia, which then means that it's easy for you to stop the cart, or make it move, or make it take a turn. Fairly easy. But now imagine that you load this shopping cart with some heavy items. That makes the cart harder to move, harder to start pushing it, harder to stop it from moving, and it also makes it harder to take a turn. And so this is only because now it has more inertia due to the fact that it has a larger mass. So that's how mass and inertia are related. So we can sort of judge if an object will be easy to move or hard to move, or easy or hard to change the direction of that object's, the direction of motion of that object, by simply gauging its mass. So heavier objects are harder to make move or stop from moving or change the direction of their motion, and lighter objects are very easy or easier to make move, stop from moving, or change the direction in which they're moving. And so we are going to deal a lot with mass during this course. So the units for mass in the metric system are kilograms, and the units for mass in the imperial system are slug. So the more common unit that we will see through the course would be the metric unit of kilograms. Now we are ready to discuss how forces affect the motion of objects with certain mass. The statement is presented by Newton's second law, which is also known as law of acceleration. So the statement of the second law is that the total force acting on a body is equal to the mass of the body times its acceleration. The formula that represents the second law is that the force F is equal to the product of the mass m of the object and its acceleration a. So what does this statement mean? It means that for an object with certain mass, when a force is applied to that object will accelerate, will move with acceleration. So when an object is in motion and it is accelerating, that means that there must be a force acting on that object. On the other hand, if an object is in motion but it is not accelerating, so it's moving with constant velocity, then that means that there is no force acting on this object, unbalanced force acting on this object. So if there are any forces applied to that object, the net is zero. So one more time, when an object is accelerating, that means that force is acting on the object. When an object is moving with constant velocity, it means that there is no net force acting on this object. Now let's look at the units. So in the metric system, force is measured in newtons, and that is a derived unit, something that I talked about in chapter 1, the physics toolkit. And so this derived unit is made from the product of the units of mass, which would be kilograms, and the unit for acceleration, which is meters per second squared. And so a newton is equal to a kilogram times meter divided by second to the second power. And this is the metric unit for force. So when we do problems through the entire course, when the units are metric, the force that is calculated will always be measured in newtons. It doesn't matter what type of force is being discussed, all forces are measured in newtons in the metric system. So I expect from you to remember that that is the unit, and anytime you do a problem with metric units, the unit for force will be the newton. In the imperial system, the unit for force is the pound, and that will be the product of the unit for mass, which is the slug, times the unit for acceleration, which will be foot per second squared. So this is the imperial unit. So again, no matter what type of force is in discussion, the unit would be always pounds in the imperial system. So let's look at one example calculation using the second law formula. What force will produce acceleration of 7 meters per second squared on a mass of 2 kilograms? So let's make a list of what we know and what we're looking for. So we know that the acceleration, A, is 7 meters per second squared. So how do I know that that's the acceleration? Well, first of all, the problem obviously states it, but even if it didn't, I know that the units for acceleration in the metric system are meters per second squared. And then the mass is 2 kilograms. And so what I'm looking for is the force. And so for force, we use in general the letter F. And now the three quantities are related through Newton's second law. So F is equal to mass times acceleration. So the force is equal to mass times acceleration. Since I'm looking for the force, the formula already is in the correct form for me to substitute the values. And so let's see what we get when we do the calculation. So I substitute the values for the mass and the acceleration in the formula. So I have 2 kilograms times 7 meters per second squared. That is 14 kilograms times meters per second squared, which we call a Newton. And so the force is 14 newtons. Notice one thing, that mass here is in the correct units, it's in kilograms. So when I multiply the two quantities and the units multiply, I already have the correct units here to form the Newton. If the mass was in different units, before I do the calculation, I must convert the mass in the correct units, which would be kilograms, and then do the calculation. If the mass units are not converted into kilograms, then the answer of the calculation will be wrong, or the result of the calculation will be wrong, and the answer to the problem will be also wrong. Now let's look at this example using, again, Newton's second law. Find the acceleration due to a 600 Newton force applied on a 3,000 gram mass. So this time we know the force, which is 600 newtons, and the mass, which is 3,000 grams, and we are looking for the acceleration A. So again, to be able to solve this problem, apply the second law, so F is equal to mass times acceleration. However, now we are looking for the acceleration, which means that I must rearrange the terms in this formula to isolate the acceleration on the right side of the equation and have the force and the mass on the left side of the equation. So since the mass is multiplying here on the right side, in order to isolate the acceleration, I would divide by the mass on both sides. So the mass on the right side is in the numerator and denominator, so that will cancel out. And so now the formula for calculating the acceleration becomes A is equal to F divided by M. Now let's substitute the quantities for F and M, and let's see what we get. Alright, so this becomes 600 newtons divided by 3,000 grams. So in order to find what would be the units for the answer, for the acceleration, I must present the newtons in terms of the units of mass times the units of acceleration. And so what I get is that 600 kilograms meter per second squared divided by 3,000 grams will be equal to the acceleration of motion of this mass. But now if I look at the units in the numerator, for mass I have kilograms, and in the denominator for mass I have grams. And so these units currently are incompatible. I can't cancel them out, which means that I must convert the mass of this object from grams to kilograms. Then I'll be able to cancel the mass units. And so let's do that. So I have 600 kilogram meter per second squared divided by 3 kilograms. Here I used the fact that 1,000 grams are equal to 1 kilogram. And so now I can cancel the mass units, kilograms in the numerator and denominator. And what I'm left with is 600 meters per second squared divided by 3. And that is equal to 200 meters per second squared. And so the units for the acceleration are meters per second squared, as expected, since this is a problem that uses metric units. So the importance of having compatible units when the calculation is done becomes clear here, because if I did not have this conversion, then I would get a different answer. If I did not convert the units of mass here, then the answer would be 0.2 meters per second squared, but that is wrong. The correct answer is 200 meters per second squared. So when you're doing calculations, and that's irrelevant of what particular problem you're dealing with, you always must make sure that the units are compatible, meaning the mass units are in the same, the mass quantities have the same units, speed quantities have the same units, so on and so forth, so that you can cancel units where applicable, and then you know that your answers will always be correct. Let's talk about the interpretation of the second law a little bit. What does that mean in terms of mass and force and acceleration? So we know that if force is applied to an object with some mass, it's going to move with some acceleration. But what exactly is the relationship? So here there are two possibilities. One would be to keep the mass constant and change the applied force and see how the acceleration changes. And the other one would be to keep the force constant and change the mass and see how the acceleration changes. First, let's look at the case where the mass is constant. I selected the mass to be 1 kilogram. And now I'm going to apply several different forces to that mass and calculate the acceleration. When the applied force is just 1 Newton, the acceleration will be equal to the force divided by the mass of the object. So that would be 1 Newton divided by 1 kilogram, so that is 1 meter per second squared. When the force of the applied force is 2 newtons, the acceleration then would be 2 meters per second squared. When the applied force is 10 newtons, then the acceleration will be 10 meters per second squared. So for the same constant mass, whatever that is, as the force increases, the acceleration increases proportionally. Now let's see what happens when the force is kept constant. Let's have a force of 10 newtons applied to an object, but the mass now will be changing. So when the mass is equal to 1 kilogram, then the acceleration will be 10 newtons divided by 1 kilogram, which is 10 meters per second squared. When the mass is 2 kilograms, then the acceleration becomes 5 meters per second squared. When the mass is 5 kilograms, the acceleration is 2 meters per second squared. And so we can see here that as the mass increases, the acceleration decreases. And then in the previous example, for a constant mass, as the force increases, the acceleration increases. So then that is sort of a confirmation of Newton's first law, the law of inertia. Heavier objects require more force to be moved, and if the same force is applied to objects with different mass, they will also move with different accelerations. The heavier objects will move with smaller acceleration, the lighter objects will move with higher acceleration. So the heavier objects, which are more inert, are more resistant to the change, to a change in the way that they move, as opposed to lighter objects, which are less resistant. So now we have one more law to discuss, the third law, which is the law of action and reaction. But before we get to that, let's look at several specific forces that are common in most everyday situations. So the first force that I want to discuss is the force of weight, or simply weight. The weight of an object is the amount of gravitational pull exerted on that object by the Earth. And if that force is not balanced by other forces, an acceleration is produced. This acceleration is known as acceleration due to gravity, and we already talked about it in the previous chapter about motion. So we label that acceleration with g, and the value of that acceleration close to the surface of the Earth is 9.8 meters per second squared in the metric system, or 32 feet per second squared in the imperial system. So any object released to free fall towards the Earth will move with that acceleration, no matter what the size of the object is. So how do we calculate the weight of an object? We simply multiply the mass of that object by the gravitational acceleration g, and that's going to give us the weight of this object. So since this is a specific force that we are discussing, I introduce a new label specifically for weight, and so that would be F sub W. So Fw is the force of weight, or just weight. What are the units for weight? Well, this is force, so therefore in the metric system, as any other force, we will measure the weight in newtons, and in the imperial system, in pounds. The definition of weight is very useful in situations where we know the mass of an object, but we need to calculate its weight for the purposes of solving a problem. And also it is useful in situations where we know the weight of an object, but we need to find its mass for the purposes of solving a problem. This particular formula for the weight is used a lot through the course, and so it is very important to remember this definition and be able to use it when necessary. And one more time, I'd like to stress that the units for weight would be newtons in the metric system and pounds in the imperial system. A very common mistake that people make is to confuse mass and weight. Those are two completely different quantities by the nature of how they are defined. Mass is a scalar quantity, which means that it only has magnitude, it only has a value, as opposed to weight, which is a force and therefore is a vector quantity, which has magnitude and also direction associated with it. Mass is simply defined as the amount of substance or material or stuff, if you want, in the volume of an object. So the amount of mass of an object is determined only by its volume and, of course, the material from which it is made. And so the mass of an object will never change unless somehow a piece of this object has been removed, as opposed to the force of weight, which depends on the force of gravity or the gravitational acceleration, and that force can change depending on the value of the gravitational acceleration. So, for example, we know that on the moon, a person would have very easy time of moving around and jumping to high heights and long distances, because the gravitational acceleration there is much smaller than that on Earth. And then on Earth, that same person will not be able to jump as high or as far as on the moon. And so this person has the same amount of mass on the Earth and on the moon, but their weight is different due to the fact that the gravitational acceleration on the moon and the Earth are different. And so the mass of an object is a constant quantity. It never changes. As opposed to the weight, Fw, of an object, which can change depending on the value of the acceleration due to gravity. And so we are going to encounter those two physical quantity, mass and weight, a lot through the semester, and I expect that you will remember the difference between the two and be able to apply the definition of weight and how it's calculated to be able to find the mass of an object if you knew the weight, or the weight of an object if you knew the mass. And one more reminder about the units. Mass is measured in kilograms as a base unit in the metric system, or slug as a base unit in the imperial system, and weight is measured in newtons in the metric system and pounds in the imperial system. Let's do a few example calculations with the definition of weight to illustrate the procedure of how we calculate using that formula. So the first example asks us to find the weight of 6 kilograms. All right, so since the mass here is given in metric units, that implies that I will have to use the value for the gravitational acceleration in the metric system. So we know the mass, it is 6 kilograms, and even though the gravitational acceleration value is not stated, we know the value of that, and that is 9.8 meters per second squared. And what we are looking for is the weight of this mass, Fw. So by definition, the weight Fw is equal to the product of the mass of the object times the gravitational acceleration of Earth. So now I will substitute the known values in the formula to find the answer to this question. So that would be 6 kilograms times 9.8 meters per second squared. This would be equal to 58.8 newtons. And so this is the weight of this mass of 6 kilograms. So notice that here the mass, as we already said, is a constant quantity, doesn't change. But if the value for the gravitational acceleration were something else, let's say the gravitational acceleration on another planet, then the weight of this 6 kilogram mass will be a different quantity. It's not going to be 58.8 newtons. So the next example will show this difference. So here's the next example. Find the mass of an astronaut if on the moon their weight is 200 newtons. And the gravitational acceleration on the moon is g moon equal to 1.63 meters per second squared. So we know the weight of the astronaut, which is 200 newtons on the moon. We know the gravitational acceleration on the moon, 1.63 meters per second squared. We are looking for the mass of this astronaut. So again, I will use the formula that calculates weight. So Fw is equal to m times g. And since I'm looking for the mass, I will leave the mass m alone on the right side of this formula and move g on the left side. So if I divide both sides by g, what I get is Fw divided by g is equal to m. And so this will be my working formula in which I can substitute the values of the weight and the gravitational acceleration to calculate the mass of this astronaut. So the calculation becomes 200 newtons divided by 1.63 meters per second squared, which is equal to 123 kilograms. And for comparison, let's calculate the weight of this astronaut on the Earth. So we have the mass, which is 123 kilograms, multiplied by the gravitational acceleration of Earth, 9.8 meters per second squared. That's going to give us 1,205.4 newtons. And so the gravitational acceleration on the Earth is roughly 6 times more bigger than the gravitational acceleration on the moon. And so as you can see, the weight of this astronaut on the Earth is roughly 6 times bigger than the weight on the moon, 200 newtons right here. The next force that I want to discuss is the force of friction. Friction is a force that arises when two surfaces are brought in contact and move with respect to one another. So the nature of friction is to resist the relative motion of objects in contact, and it is caused by irregularities in the surface and also by adhesion forces between the molecules of one surface and the molecules of the other surface. So friction can only arise when an object is moving across a surface, so there is contact between two surfaces, and friction always opposes the direction of motion. So here in this example, this block is being pushed to the right, and so since it slides across a horizontal surface, a force of friction arises between the block and the surface, and the force of friction is directed to the left. It opposes the direction of motion. So the reason for the force of friction to arise is the surface irregularities between the two surfaces in contact. So in this picture here, we see that there is a mechanical contact between the irregularities of the two surfaces. And so when two peaks meet each other, they will essentially grind against each other, which then slows the motion of the two objects with respect to each other, and that is part of the force of friction. And the other part of the force of friction is the adhesion forces between the molecules from one surface and the other surface. So those adhesive forces are similar to electrostatic forces between charged objects. So we have two surfaces in contact with each other, surface 1 and surface 2, and this is the interface between the two. So let's look at the molecules from each surface. Let's use blue for the molecules on top surface, something like this, and so on and so forth. There is an infinite number of those, essentially. And then on the bottom, we have different molecules, which can look something like that, depending on the materials used. And so on and so forth. Well, so when the two surfaces are very close to each other, there is a lot of contact area between the two surfaces. And these molecules from surface 1 and surface 2 are going to bond with each other with those adhesive forces. And so you can think of them as if they're being connected to each other, like so. And so if the two surfaces are to slide across one another, then those bonds must be broken. And so for the macroscopic perception of what's happening, this is also perceived as friction. So one more time, friction is the combination of two separate processes. One is mechanical interaction between the two surfaces due to irregularities in the surfaces. And the second is adhesive forces arising between the molecules of the two surfaces when the two surfaces are in contact. Now, depending on whether you have more surface irregularities or smoother surfaces, one of the two mechanisms responsible for friction will dominate. So for surfaces that are rough, we have more of a mechanical interaction than bonding of molecules. For surfaces that are very smooth, we have more of a adhesive force action rather than mechanical interaction. How can friction force be changed between two surfaces, increased or decreased depending on the application? Well, if we want to decrease friction, the surfaces of the two objects that will be in contact can be smoothened. So smoother surfaces will decrease the mechanical interaction between the two surfaces, which will reduce friction. Another option would be to also use lubrication. And as you know, in car engines, oil is used to reduce friction between parts, which then also increases the longevity of the parts. So it decreases the abrasion, the use of parts. And finally, different materials can be used to reduce friction. So for example, Teflon is much more slick compared to, let's say, steel or copper. So if you can make parts that are made from Teflon instead of, let's say, steel, that will reduce friction. And of course, depending on the application, it's not always possible to use the smoothest, the slickest possible materials that produce the least amount of friction. But when materials that are suitable can be found, then they can improve decrease the friction between parts. And why is that important? It is important because it reduces heat production, which means less loss of energy, which means better efficiency of the device that's being optimized. And also it might mean cheaper cost of production. Now, what happens if the two surfaces are made really smooth? Well, there is a diminishing returns point past which the surfaces get so smooth that then you will get a predominant adhesion effect between the molecules of the two surfaces, which will then increase the friction between the two surfaces. For example, if you take two panes of glass and press them against each other. Glass is extremely smooth, and so a huge amount of adhesive force will be created between the two panes, and essentially that will generate a giant amount of friction force, and it's going to be essentially impossible to slide the two panes across each other. So there is a trade-off between surface roughness and the amount of friction that is generated due to that. Now let's discuss how we can calculate the force of friction. So for this purpose, I'm going to draw a schematic of an object that is resting on a flat surface. So here is my flat surface, here is my object. Think about a wooden block, for example, and this wooden block has a mass m. Alright, so since the block is at rest, there's only two forces that act on this block, and those two forces are the weight of this block, which is straight down, and so that weight pushes on the surface here, on the bottom surface, and then as a result, the bottom surface pushes on the block with equal by size but opposite in direction force, which we call the normal force. So the two forces, the normal force Fn and the force of weight Fw, are equal by magnitude and in opposite direction. So if the two forces are added together, they will cancel out and they will produce a zero net force applied to this block. Okay, so now if I want to move the block, I must apply a force, and let's say that this force is applied to the right. And so as a result, the block is in motion to the right. Well, since there is contact between the block and the horizontal surface, that will then create a force of friction between the block and that surface. And so this force of friction will act opposite to the direction in which the block is moving. So the force of friction will be directed to the left. And I'm going to label this force with F sub F. So that is the force of friction. So through experiment, people have found that the force of friction is proportional to the normal force. So the force of friction is proportional to the normal force. Well, it turns out that the coefficient of proportionality depends on the materials that are in contact, and this coefficient is called coefficient of friction. So the force of friction Ff is equal to a coefficient of friction mu times the normal force Fn. Mu is the coefficient of friction, and as the name suggests, this is just a number, it has no units. The coefficient of friction mu varies by value depending on the materials that are in contact. And now let's look at the different forces of friction that can arise based on the type of force that's applied to an object. So first we have static friction. So this is the force of friction that arises when a force is applied to an object, but the object is not sliding across a horizontal surface. So for example, imagine you have a crate that weighs 400 pounds, and you are applying force to push it across a horizontal floor, but this crate is not moving. Well, since you are applying force to the crate, that means that there is a friction force between the crate and the floor that opposes your force. And so the only way you would be able to move that crate across the floor, to push it across the floor, would be if you apply enough force to overcome the force of static friction. So This is a different situation compared to the crate resting on the floor and nobody's pushing on it. In that case, there is only the force of weight on the crate that the crate applies on the floor, and then the normal force with which the floor pushes on the crate. But once force is applied horizontally to try to move the crate, a force of friction arises between the crate and the floor, and this force is known as the force of static friction, and it remains such until the crate starts to move. So static friction arises when a force is applied to an object to move it, but the object is not moving because the applied force is less than the force of the static friction. So to sketch the example, here is my crate resting on the flat surface here, and now force F is applied, but the crate is not moving. That means that there is a force of friction that's generated opposing the action of the applied force F, and that force of friction is static friction. So how do we calculate the static friction in those cases? Well, we already discussed the formula that calculates friction, so that is what we use, and that is the coefficient of static friction mu multiplied by the normal force. Once the applied force F becomes larger than the maximum possible static friction force between the object and the surface, now the object will start to move. And then in this case, the friction becomes a different kind of friction, which is known as kinetic friction. And kinetic friction is smaller force than static friction, which means that it takes more force to make an object move to overcome static friction than it takes to keep the object in motion once it is moving. So a force F is applied to the right, the crate starts to move to the right. As a result, there is a force of friction between the crate and the floor, and that is now kinetic friction force. This force is smaller than the static friction force between the crate and the floor. So how do we calculate the kinetic friction force? Well, the same formula applies. The kinetic friction force Ff is equal to the coefficient of kinetic friction mu times the normal force. So the formula for static friction calculation and kinetic friction calculation looks exactly the same. So what's the difference? The difference is the coefficients of friction. So for static friction, we can label this as mu sub s, the coefficient of static friction. For kinetic friction, we can label the coefficient of friction as mu sub k, coefficient of kinetic friction. And so the coefficient of static friction is a larger number compared to the coefficient of kinetic friction. Finally, I want to introduce an actual working formula that can be used to calculate the force of friction. And why do I need to do that if I already defined force of friction as the product of a coefficient of friction and the normal force? Well, because typically the normal force is not known, but what we would know about an object is either its mass or its weight. And we also know from the previous slide that the normal force is equal to the weight of the object. So therefore I can replace the normal force in each of those two formulas with the weight of the object. And so then the force of friction will be calculated as the coefficient of friction times the weight. We also know that the weight is calculated as the product of mass and gravitational acceleration. So the force of friction would be equal to the coefficient of friction times mass times gravitational acceleration. So these two versions of the formula for the force of friction are the true working formulas that are used to calculate the force of friction. And so if you had a problem in which you know the weight of the object and the coefficient of friction, then you can calculate the force of friction. If you had a problem in which you knew the mass of the object and the coefficient of friction, then if you multiply the two and also multiply that by the gravitational acceleration, you would be able to calculate the force of friction in this problem. You can also have the opposite question, which would be, if you know the force of friction and the coefficient of friction, what would be the weight of the object? Or, if you knew the force of friction and the weight of the object, what would be the coefficient of friction? And then from the second formula here, you also would be able to answer the question of what is the mass of the object, if you knew the force of friction and the coefficient of friction. So those two formulas essentially can solve any problem regarding the force of friction. Let's look at one example of calculating the force of friction. So a force of 170 newtons is needed to keep a 530 newton wooden box sliding on a wooden floor with constant velocity. What is the coefficient of friction? So we know that the force that is keeping the wooden blocks in motion is 170 newtons. The weight of the box is 530 newtons. We are looking for the coefficient of friction. Now, one thing that we don't know is what is the force of friction between the box and the floor. This is not stated. However, the wording in the problem tells us what the force of friction is. And this wording is that the box is sliding across the floor with a constant velocity. Okay, so constant velocity. What does that mean? It means that the force that is pulling or pushing on the box is balanced by the force of kinetic friction. So therefore, the force with which the box is being pushed or pulled is equal to the force of kinetic friction. And because of that, there is no acceleration, which means that the box is moving with constant velocity. Remember, this is basically the statement of Newton's first law. And so I will use that to solve the problem. So basically the force of friction is equal to that force, which is 170 newtons, because the velocity v is constant. Okay, so now I know the formula for calculating the force of friction, and that is that Ff is equal to mu times the weight. I know the weight, I know the force of friction, I'm looking for the coefficient of friction, so I'm going to rearrange the terms here. So the force of friction divided by the weight is equal to the coefficient of friction. Now I can plug in the numbers to calculate the result. So that is 170 newtons divided by 530 newtons, and this is equal to 0.32. And as I pointed earlier, the coefficient of friction is just a number, it has no units. Another thing that I must say is that the coefficient of friction is always less than 1. If you get a value that's more than 1, that means that you've miscalculated. So mu is always less than 1. Always. Now I want to ask an additional question. What is the mass of this wooden box? Well, I can calculate it from the formula for the weight. So the weight of the box is equal to the mass of the box times gravitational acceleration. And so the mass is equal to the weight divided by the gravitational acceleration, which will be 530 newtons divided by 9.8 meters per second squared. And this is going to give me 54 kilograms. So this is how you essentially would approach those types of problems. You have to be careful about words such as constant velocity and what that means. and just apply the formula for one of the two formulas for calculating the force of friction from the previous slide. And always keep in mind that the coefficient of friction is less than 1. And always keep in mind that the coefficient of friction is just a number and it doesn't have units. All right, so now what's left to discuss is Newton's third law, or also known as the law of action and reaction. The statement of Newton's third law is that for every force applied by object A on object B, and this force is known as action, there is equal but opposite force extended by object B on object A, and this force is known as reaction. So let's give a few examples of action-reaction forces to illustrate this law. So the first example we've already discussed several times in different contexts. That would be a block that is resting on a horizontal surface. So the block is applying force on the surface, and that force would be the weight of the block. And so as a result, the surface pushes back on the block with what we know is the normal force. Those two forces are equal by magnitude and directed in opposite direction. And so they cancel each other out. And as a result, from the first law, this block is not in motion. And so here in the statement of the third law, the weight of the block is the action force, and the normal force from the surface is the reaction force. Here is a different example. So we have a vehicle that is moving on a horizontal road, and the vehicle is moving to the right. Okay, so we know that there is friction between the wheels or the tires and the road. Okay, but in what direction is this friction? This is very interesting. So since the tires are spinning clockwise here, the direction of relative motion between the two surfaces would be the rubber of the tires is moving that way, and so therefore the force of friction is actually directed forward. And actually that is the force that makes this car move in that direction, to the right. This is very counterintuitive because we said that the force of friction arises in a direction opposite to the direction of motion. However, here that motion that is stated in the definition is the relative motion between the tires and the road, not the car and the road. That's two different things. And so this is a reaction force here that is responsible for the motion of the car. The last example would be the gravitational force between two objects, for example, the Earth and the Moon. So the Earth pulls on the Moon with some gravitational force F, but we also know that the Moon pulls on the Earth with gravitational force F. So this is the force with which the Earth pulls on the Moon, this is the force with which the Moon pulls on the Earth. And so as a result, the two bodies orbit about a common center of mass. And this common center of mass is shifted from the center of the Earth a little bit by a few hundred kilometers, I believe. But because of those two forces, action and reaction force, that's why we get this orbital motion. How do we know that the Moon is pulling on the Earth? Well, the oceans experience tides. And these tides are due to the fact that the Moon pulls on the Earth. Since the water on the Earth is, much less than the entire, Earth, the mass is much smaller. It's much easier to move by the gravity of the Moon compared to the entire Earth itself. And that's why we see those tides. So that is a piece of evidence that the Moon gravitationally pulls on the Earth. So the gravitational force between two objects is an example of an action and reaction pair of forces. All right, so this concludes the lecture on force. And next lecture will be on momentum and impulse.